some things that Greg mentioned. For the first collaboration, we made a conscientious decision to keep the size very small. We could have had 3 times as many people. We just invited a bunch of people like Paul, Emilia, Stefan, and Steve to give us honest feedback about how we're doing or what we're proposing as a first step in the collaboration to make sure they were actually keeping some promises or at least we're on the right track of doing that. So please, to the external reviewers, don't be shy. Just tell us if anything that we're doing is not on the right track. Second of all, well, this is, Paivias went through this yesterday. This is the collaboration with Paivi and Andrei as co-directors, which has proven very successful at managing this, I think, so far. And these are our goals. Everybody remembers them. I want to go very quickly through the goals. As you can read them, you probably read them already, but I want to go to the promises. And one of our major promises, highlighted here in red, that we are going to predict specific materials with superconductivity and unprecedented high temperatures. So I would like to at least try to keep some of these promises, especially this one, since there's only 2 promises, right? This is 50% of what we promised, so we should try to keep it. I think basically we don't need, obviously, to give something at room temperature the first year, but I think at least we should try to predict some outliers, right? At least predicting outliers. For example, anything electron-phonon coupled above 20 Kelvin or above 10 Kelvin even is an outlier. So trying to predict new outliers that actually get realized is something that I would be very, very happy about as a beginning, because it would mean that we sort of start to understand what it takes to do this. So with that, I wanted to get right in the talk. I took Greg's advice of not putting 2 talks in my talk, but I put 6. So basically, I'm just going to give you, most of this is unpublished, so it's just collaborations. A lot of the stuff has been done by Jonah, Dumitru. How are you? Is going to leave soon. Jonah is in his last year. Dumitru already left. But I'm very blessed with the new group of people that I'm collaborating with that are doing a lot on the AI part. Hangshi and Junze, and a bunch of collaborators either from Peking IOP, one of my friends from grad school from Su Sheng's group who was doing a non-compete for 2 Sigma now, and of course Nicolas, who's also interested in these AI. So I'll get to it at the end, hopefully. So I wanted to talk about several things. I kind of agree almost 99.9% with what Paivi said. Yes, super rich phase diagrams, maybe not the place to look for exactly the highest TC. I mean, super rich meaning, a huge parameter space. But, the first rule of a rule is to break it. So I'm going to talk about a little bit about exotic superconductors, and mostly about just rhombohedral graphene in a certain regime where I hope the situation is clean enough that something very clear can happen. Then I'm going to talk about understanding one outlier in superconductors without ab initio, and this is the outlier everybody knows, it's MGB2, but we're trying to understand it we're doing the minimal amount of ab initio that's possible, trying to understand it analytically in order to be able to predict new ones. This outlier cannot be predicted by machine learning. It never is predicted by machine learning if you don't put things with MGB2 in the training set. Then I wanted to talk a little bit about understanding some failures, and that's related to Oscar's talk yesterday. That kind of got me thinking about our failures in some of these materials. And then I'm going to talk about understanding some flat bands in resistive materials, putting some bounds on superconductivity, and finally present some new results that we have using AI. And as a reminder of the peril that AI can bring while making slides, which will be given in the last slide also. Now I'm going to talk first about the Berry trash can model. This is an AI-generated slide, which supposedly, I hope, will be able to at least explain parts of superconductivity in rhombohedral graphene at high displacement field. These are the young people that were working on this. The people that have positions are here, and also there's related work by Vitero, Paco, Guinea, and many others. But basically, the moral of the situation, this is exotic superconductor, never going to be, high temperature. But I think it's very interesting, so I'm taking 2 minutes to talk about it. Rhombohedral graphene, 5 layers, 4 layers, 6 layers. You put a displacement field, you separate the bands, you put a moire on the bottom away from the conductive layer. You see fractional churn insulators. It was early on predicted by Jonah, Jab, and even Nicola that these fractional churn insulators cannot exist without moire, and it's not an effect of just pinning the moire. It's actually pinning an anomalous Hall crystal. It's actually a real moire effect through the Coulomb interaction. After this was predicted, the experiments came in untwisted, so no moire, pentalayer graphene and 4 layers, and then they don't see an FCI, but they do see a superconducting regime. And this superconducting regime, I want you to notice, I'm not going to talk about these superconductors, SE2, SE3, forget about them. I'm going to talk about the big one here. Notice the density range. There's a density range. This gives a scale. What is the scale? So these graphene layers have trigonal distortions, have a lot of complicated things. But what I want to argue is that this scale, or at least the first incarnation of this scale, just gives you a density, it gives you a momentum space cutoff. And in this momentum space cutoff, it gives you the hint that there could be something very simple or very simple Hamiltonian happening in this system. Also, the system is valley and spin polarized, because that density has to do with where the bands in a displacement field, this is the gap. If there wasn't any displacement, it would be k to the 5th. This is the band in the displacement field. Displacement field creates a flat bottom. This k to the 5th, if k is less than 1, is basically flat at energy displacement field. If k is greater than 1, it shoots up. So k equals 1 is a preferred density. K equals 1 is actually T perp over VF of the order. In 5 layers is 0.5, T perp over VF, but it's basically of that order. Now, this looks like a trash can, the dispersion, so we call it a trash can. But the more important thing is that this part, the flat bottom of the trash can, has a Berry curvature. And this Berry curvature is constant in momentum space, or almost constant in momentum space. And it's given by VF squared over T1 squared, so basically KB squared up to factors of 2 pi. For 5 layers, the entire Berry flux contained from here to here, notice the gapless system, is pi over 2 of the order. If I had an infinite number of layers, it would be 2 pi, because these would be drumhead states. What I also want to point out related to yesterday's talks is that while, of course, here, these states at k equals 0 are polarized on the surface, as they get closer to here, they go into the bulk. So for k equals 1, for example, so somewhere here, the states become not polarized on the surface. It's very similar to a topological insulator situation, where you basically, as you go away from momentum of the Dirac cone, the states become closer and closer polarized into the bulk. So the fact that you have a Berry curvature here, constant Berry curvature, gives you form factors. And if you go in one valley, one spin, so quarter metal, polarized situation, which we do seem to be in, because that density that you see here is actually, it matches almost perfectly to this. It's not 4 times this. It's roughly this density, where the superconductivity stops, or 0.9 times the density. Then you're going to get these form factors, which you recognize. This VQ is a potential. It's Coulomb potential. If it's repulsive, really in the samples is some screened Coulomb potential. But these form factors are the Gervin-Plassman-McDonald algebra. And the reason for that is the fact that you get a constant Berry curvature. So this situation looks similar to the quantum Hall effect, except it's a gapless system, and the Berry flux over this region where it's flat before the dispersion shoots up is not quantized. Why do we like this model? Well, this model starts having nice properties when this velocity, which is actually the Dirac velocity of the trash can, goes to infinity. When this velocity goes to infinity, it's almost solvable. Okay, and you can ask, of course, it's a single particle, it's a many-body model, it's not a single particle, it's a many-body model of single flavor. So even if it's superconductor, it can only have some odd pairing. But you can ask whether you can have px pairing, py pairing, px plus ipy, px minus ipy, px plus ipy cubed, etc. And to do that, we just take a short-range attractive interaction. Now, this doesn't depend really on the short range. Just any attractive interaction you take, you'd get similar things. But the exact solution does depend on this. So we don't know where this interaction comes from as negative. But the question we ask is there some universal statement that you can make when it becomes negative? And the universal statement that you can make is that now the two-body spectrum you can solve. And it looks like this with a pairing term, which is P plus IP. So the pairing term, the lower state, so it's got many pairing, K plus to the M, but the lower state is M equals 1, and it locks with a Berry curvature in the bottom of the trash can. That's the lower state. And then the model I showed you before, the one with the Gervin plasma McDonald, actually to the first order in the Berry flux, which, you know, at pi over 2, Berry flux over 2 pi, at pi over 2, you know, you can argue that you can use the first order. You can get an ansatz for the superconductor, which is exact to first order. It's very good, 99% overlap to, or 98% overlap to full order, which is just this sort of eta pairing operator to the nth power on the ground state. And you can see the binding energies. So it superconducts, okay? So now, yes? Well, it's not pi eta pairing. It's just generalize, you know. Exactly. So it's not the Young eta pairing. I'm just abusing language because why not? Okay, very good. So with repulsive interactions with Nikolai and Hekshu and Jonah and Eve, other people, we're solving the model. It seems to also have some states that can be solved. So we'll get back to you later. But basically, if we can find with repulsive Coulomb interactions superconductivity, then we can say exactly, then we can say, you know, we're not going for conlatitude, or we don't have to accept the approximations of conlatitude, we can just find exactly. If we don't find it, then we at least know that maybe electron-phonon coupling is important. And I want to come back to Eret's point yesterday, what I agree with him that, you know, if you take the conventional you know, slope of the phonons, they will be unimportant. These superconductivity, at least in these flat bands or transport, is very unconventional. Obviously, superconductivity is unconventional. So I think we should be a little bit agnostic about what the source of superconductivity is in the systems. I agree that it could not be phonons, but I think it's not completely ruled out. Okay, so that's the end of my exotic superconductors. The next thing that I wanted to do is, that we wanted to do is to understand MGB2. And this is really a collaboration spearheaded by E and How Are You, with help from Hangxi and Dumitru. But basically, this is an outlier. As you know, I mean, you can talk to Miguel, but you can talk to anybody that has done a little bit of superconducting temperature prediction. If you don't include any of the MGB2 doped systems in the AI, it will fail to predict this because it's an outlier. So it won't know the TC of this guy. Okay, so what we try to do is to play this exercise of understanding MGB2 without resorting to DFT. And something interesting came, and I have an update for a question that Päivi asked in a previous conference. So basically, the moral of the story, MGB2 per layer is not a layered system in the sense of van der Waals. You can't separate it, but it's got layers, it's got mass separation of boron and Mg. It's isoelectronic to graphene, so the same electron number for borons because Mg gives electrons. So now the boron has sp2 hybridization. The sp2 orbitals on site move to the 3 orbitals here, and you immediately see the covalent bonding nature of the system. There's a duality in the system that basically the hopping between these orbitals that are s orbitals away from the boron, so 3 s orbitals away from the boron, representation-wise equal an spxpy orbital on boron, the hopping between these becomes the gap of the bonding, anti-bonding of the Kagome site, and the on-site difference between S and P here becomes the bandwidth of the bonding, anti-bonding bands. And the way you can, you can get this from DFT, but you can actually evaluate this up to 30% by just doing hydrogen orbital overlaps. 30 or 20%, I don't remember. So you can evaluate them quite accurately by doing orbital overlaps. Now, if this covalent band did not come to the Fermi level, MgV2 would have completely bad superconductivity because the pz orbitals of graphene or a boron don't really couple strongly to this phonon, which is just a covalent bonding phonon. So most of the superconductivity in MgV2, this is ab initio, comes from here. But if we try to understand why this band comes to the Fermi level without doing ab initio, then we actually turns out that we can understand it, right? You can see very large, small density of states. It's just very strongly, these are the sp2 bands. These are the pz bands, even though large Fermi surfaces, 7% of the superconductivity or 8% of superconductivity is on them. 90-something 2 is here. Why does it come to the Fermi level? If it didn't come to the Fermi level, it would be like graphene, 0 Tc. Obviously, density of states also, not 0 Tc, but much lower. In any case, why does it come to the Fermi level? We can estimate that the sp2 band has to come to the Fermi level in this situation because the pz orbitals from boron are out of plane. Because they're out of plane, they couple strongly to the Mg orbitals, which pushes down, okay, the pz levels of boron. Hence, if I want to keep isoelectronic number, if I want to keep stoichiometry, I have to bring up the sp2 band to pick up the slack in the electron number. Notice that the sp2 orbitals of these boron do not couple strongly to Mg because they're in plane. Pz couples more strongly, Pz gets pushed down, the sp2 bands come to the Fermi level to pick up the electron number. We can even estimate this density, I don't know, 50%. Of course, not everything is very accurate by just doing hydrogen orbital overlaps, right? Because we're doing a very crude approximation. So we can understand why this comes to the Fermi level. Once we understand why this comes to the Fermi level, we must understand A, the phonon spectrum, and which bands couple to the phonons. Well, we know the bands that couple to the phonons are the sp2. I want you to remember this double vortex here because it will be important. There's a double vortex here coming from a Kagome band. Double vortex means the wave function of these bands is k-dependent, means large quantum geometry because the derivatives of the wave functions are large. But let's go to the phonon spectrum. This is the phonon spectrum of MgV2. Looks slightly complicated, but in effect, it's not that complicated, and you can get it also, at least in large, in the zoomed out version, also from ab initio. Why? Well, I know how to get the graphene spectrum from just a spring and balls model. I just put some springs, and I can get basically, maybe I get this one above this one. These small energy differences, doesn't matter. But these ones, I can get them, the same shapes, and the representations, I can get them by utilizing the Bilbao crystallographic server, which are just a representation of a vector on the carbon side. So these are the representations come for free. Just now that the Bilbao crystallographic server is actually back online, you can just read them off. And the energies, you know them basically, or at least you know the energies, whether this one is above this one, because this one needs to be a vector, so it's going to be odd under inversion. So anyway, so you know basically most of the features of this. You can even estimate this value by doing some Born-Oppenheimer with with a pen and paper. So if I know the spectrum, I claim I now know the spectrum, and I claim this is a universal principle for things that are layered and have mass differences. Why? Well, notice that Mg is much heavier than boron, and Mg is in between the planes of borons. We are able to prove analytically a statement that when you have, say, some layer, you can just compute the phonon spectrum of the layer, i.e. graphene or boron, hexagonal boron, let's say. Then, if you want to intercalate it in between something that's heavier, the heavy part will just form the acoustic bands, i.e. Mg is mostly here, and the light part, boron, just goes up, shifts up, and moves above the acoustic part. That's a principle of what happens when you take a mass separation. You just take the layer and put it up. And indeed, if you notice that this blue has basically the same features here. This one is this one has become this one. You notice that there's a dip here, which is due to the strong electron-phonon coupling. This is a renormalization of this strong electron-phonon coupling because of the gamma Fermi surface, which we can also get in first order if we're going to do phonon self-energy. Next thing is which phonon couples. So we can get this spectrum, roughly. Which phonon couples? Well, that's very simple. First of all, physically, we know which phonon couple is the bond-stretching phonon, because the charge center is on the kagome, right? It's moved away from the boron. It's the bonding state of the kagome. So that's the phonon that will couple. But we don't need to do physics. We can just do math. So the moral of the story is that, as I showed you, the sp2 Fermi surface is tiny. If sp2 Fermi surface is tiny, the only phonon that can scatter k2 minus k is a low q phonon. So I better look at the phonons around the gamma point in plane. So, gamma a axis. And indeed, if you do ab initio, these phonons are the ones that are important. And there are several phonons here that are important. For example, there's this one, there's this one, there's this one, there's this one, there's this one. But there's a very easy group theory way of understanding which one is important, because the representation of the Fermi, of the double vortex, is gamma 5. I have 2 electrons, gamma 5, gamma 5. I have to couple it to a phonon. I want to know which scalar comes out of it. It turns out the only one that can couple, so I have phonon, electron, electron, is gamma 5, gamma 5, gamma 5 will give you a scalar, is the gamma 5 phonon that couples. That phonon is this guy, and it's actually the same guy that shows up here. Okay, so all of these we can understand without ab initio, or with a very, we need ab initio to tell us that the material is stable, okay? Because I wouldn't, obviously, if I just saw it, I wouldn't know it's stable without ab initio. Now, what is this useful for? Well, are we doing just reinventing the wheel? What I claim it's useful for is a prediction which is very counterintuitive. This prediction says the following. I'm going to dope the system now with electrons, right? So you use analytics usually just when the phase space is too large and you can't do computations for every little parameter in a phase space. So now let's use doping here as a parameter. But I want to make sure that we understand that this doping is doping like the 2D people, like Stefan, would dope his systems by gate doping. Now that cannot be done in MGP2, but it's important that that's the calculation being done. We're not adding impurities. And I'll come back to that later. What happens is you add electrons to a system, you make the Fermi surface smaller, you lose density of states, you expect TC to go down. TC actually still increases up to here, and then it goes down, of course, when you lose all the sp2 Fermi surfaces. And that, we claim, is a pure quantum geometric effect, because the double vortex that I showed you in the wave function at the gamma point has quantum geometry, because the wave functions change as a function of k, and the quantum geometry gets larger, of everything gets larger as you go to the degeneracy point. And because it gets larger towards the degeneracy point, for a region of parameter space, it's able to overcompensate the decrease in density of states. Now, why is this prediction, why I think it's interesting? Well, all the experiments that we know actually contradict it. Okay? But the experiments that we know, so MGP2 has been doped, many things, but the experiments that we know is substitutional doping. It changes the lattice constant. It induces, for example, if you dope iron, it induces spin. So it's not the kind of doping we predict here. Now, there are experiments on thin films that we found recently, and this comes to the question that Päivi was asking in a previous conference. And those experiments, they put strain, and they kind of change the Fermi surface without actually adding stuff substitutionally and messing up the band structure. In those cases, the TC does go up. It goes up to 42 Kelvin. It's not as, it goes up by 3 Kelvin. So it's not as high as this prediction, but also it might not be as high as, it might be here. So there are experiments where this happens, where you're not messing up the sample. Yes, sorry. It's a very good question. So we need, so I don't know. we need more data to actually look in. I mean, I could say it's a generic effect because it always blows up, but I don't know if I take, k cubed or some other densities. It's got to be some density of states form versus the quantum geometry, right? Some of them, that's a very good question, actually. I haven't thought about it, but it's how the density goes down versus how the quantum geometry blows up. I haven't thought about it. Very good. Yes? Yes? Very good, yes, yes, yes. So the TC, so if you do DFT in Eliashberg, it always gets you lower TC in MGB2 than it is, as far as I remember. But E, how do we get so Paul is complaining that it's not the experimental TC, and I agree with you. Okay, this is just from the SP2. We're just plotting the SP2 Fermi surface here, or E is plotting the SP2 Fermi surface.
These are theoretical.
It's a theoretical TC.
No,
DFT,
I understand.
and it's only taking the SP2 Fermi surface. So there's another TC from the PZ. There's another extra, right? There's another 5 or 3 Kelvin or whatever from the. But I wouldn't expect that. I would, the numbers I wouldn't argue against you on. Okay, I would argue about the increase. Okay, of course I'm not getting, Yeah, I mean, I'd say 30%. Yeah. I mean, I'd be happy if we could get trends with a 30%. Personally, I'd be happy with a 30% accuracy. I totally take that as a good criticism. We got to do better in terms of actually predicting numbers, but for what I'm doing here, which is very crude, or doing here, which is very crude, it's good enough for government work. Prove my point. This is getting recorded. Okay, so understanding failures. Sorry. Yes.
You didn't answer the question. With all of this effort, which is lots of post priori rationalization.
Exactly.
Can you now predict it with?
Now.
Okay, fine. So it's still an outlier.
I agree.
Okay,
Yes.
because a lot of what you're doing is what was done in the first years afterwards. Of
Not this.
not this, but
This was exactly, people actually thought exactly the opposite.
15 minutes of discussion.
So I agree. No, but this is good. This is good. So, Paul, so the answer to your question is we cannot predict outliers, and that's something that we want to.
Right. So if we have discussion, I can suggest another outlier too, but we'll.
That would be great. Yes, yes. We've made a list of some outliers, but we obviously don't know all of them, so we want you to.
I have a little list.
Very good. Yeah. Okay, so understanding failures. This is a failure for us. We couldn't understand it. Is basically hafnium or zirconium doped, lithium doped. These class of superconductors with rather high TC upon doping, that you basically get, what Oscar was talking about there. It's a massively massive Dirac point here, and you dope it to about 100 milli-electron volts, and the omega of the phonon that's involved is about 70. So you're kind of in the regime that Oscar was talking about. Oscar was talking EF smaller than omega, but again, it's good enough. So if you just do electron phonon, you do get completely mismatching TC. There's actually papers in the literature that say it's not electron phonon. There's papers in the literature, which Jon pointed out yesterday also, that do get the correct TC with some RPA. But what I'd like to understand is some rule of thumb, like if I want mass, like the reason why I liked Oscar's presentation yesterday is a rule of thumb. If the mass is large, then I'm going to get this logarithm, and I can evaluate it at least ratios of different temperatures based on the mass. So this one, I think it could be a very good collaboration. This was a failure. There's many other failures, but now I'm going to go to understanding flat bands. And we've been trying to understand with Miguel, Paivi, Christian, and Tiago. We're trying to understand flat bands and whether they are good for superconductivity. Oh, only 5 minutes, okay. And the answer is they could or they could not, and this is based on work by Jonah Haoyu and E. Junze and Hangshi. But the moral of the story here is that, it's kind of an obvious moral of the story, is the same superfluid weight, the same quantum geometry that gives a superfluid weight in a superconductor will give you spin stiffness with positive interactions, with repulsive interactions. So if you have a system that's actually fractionally filled at filling half or whatever, it'll either magnetize, ferromagnetize if you got large quantum geometry, anti-ferromagnetic if you don't have large quantum geometry, but it, won't likely superconduct. So that's the reason why a lot of these Kagomes, flat bands, are not at the Fermi level, they ferromagnetize. There are some Kagomes where flat bands are at the Fermi level and superconduct. This is one example. It was the only example until 2 years ago, or 1 year ago. Now there's a couple more examples. But this is a Kagome where the flat band is almost fully occupied. If it's almost fully occupied, the ferromagnetic tendency or antiferromagnetic is very weak, and you do get superconductivity, and we can understand this superconductivity done in work by Ian Junze and Haoyu and other people, but basically we can understand it as electron-phonon coupled. We get a very good value for TC as electron-phonon coupled. Now, I got two more things, maybe bounds. So this is coming back to Eric's talk and Steve's bound statement. So what we're trying to do is just try to understand why Miguel sees, you do AI, and you see only very few superconductors at high TC. So there's obviously probably a bound, and we're working on bounds that are basically related to what Steve, you can see by the fonts in this paper, how old this paper was, that Steve found with between the gap of a material and its Vania spread. And these bounds have been recently rediscovered, but basically come from Steve's paper. And then they're larger than the quantum geometry in papers by Resta, and then larger than the Chern number. But there's a more recent bound done by Jonah here that it's actually larger than the Wilson loop winding. So you don't need to have Chern number. Any Wilson loop winding, absolute value of the Wilson loop winding, will bound this. Now for physical applications, this is very good for collective modes as pioneered by Pivy, and for conductivity bounds by the people here. Now what we wanted to do is, again, to get some sort of a theoretical model of the electron-phonon coupling. And this is, again, a theoretical model that we get by just assuming that the orbital overlap is a Gaussian between two orbitals. It's not a Gaussian, it's usually e to the minus r, but if you assume it's a Gaussian, you have analytic expressions, and that's how we do all the analytic stuff in MGB2 or the other superconductors. We just assume this, and once you have this, then you can immediately get an approximation for the electron-phonon coupling, and that approximation is that the electron-phonon coupling, because if this is Gaussian, the derivative is just r. If you go to Fourier space, it becomes a derivative in momentum of the Hamiltonian, so you can separate it into energy derivative and a projector onto the eigenstates derivative. That's the geometric part. That's the energetic part. And this is really, this part is the reason why MGB2 has that large, increase in quantum geometry as you go towards the node, and hence an increase in TC, even though density of states goes lower. If you put this, you ask which part of these two is more predominant. In graphene, for example, doped graphene, you can do an electron-phonon coupling. I'm not claiming TC here, just electron-phonon coupling. They're half-half. In MGB2, again, what I showed you before comes out here. The geometric part is 92% of this thing. Okay, so with this, you can get some bounds, but maybe I want to get to AI in the last 3 minutes. Okay, so now when we started this collaboration, we started talking to Miguel, for which we're always deeply grateful. But then we decided to go our own into AI not because we want to compete with Miguel, but we just couldn't get Miguel on email at the rate of 5 emails a day. So we just tried to do our own AI, also encouraged by Miguel and with his him giving us explanations. So this is done by Hangshi and Junzen's a bunch of other people. But basically, first thing that we tried to do is understand what AI gives us. And that's a huge process. We didn't understand it yet. But the first thing that it does is, of course, it gives you substitutional. So you train it on this, and it gives you this. Because it immediately knows that you trained on this and some others, and it gives you this because it just substitutes the things in the columns of the periodic table. That's not very interesting. And then material generation. And this is a paper. This is an example of what MatterGen, the Microsoft program, does. I know Miguel has much better programs than this, but we don't have those. But so we trained MatterGen, and we try to understand what it does. And in fact, the way MatterGen generates you materials is the same way it generates pictures of cats. Okay, you're trying to get pictures of cats on Google. It'll generate a picture of cat. It's basically a reverse diffusion process. It learns the diffusion process from data to noise, and E and Hangshi have a very good demo of this on just two dots of how to do it. And this, it learns all the probabilities. Then it starts from noise, and it goes back to data. So it basically understands a distribution, and it tries to generate materials with that distribution. Okay, so it's not really artificial intelligence. It's mostly kind of matching a distribution. So that's what it does. It takes a stable material, puts some Gaussian noise, immediately goes into a random, after many steps goes into a random material, learns all this process for many materials, and then it tries to go back. What does it get out of this? Well, what we did, and we're probably the 1,000th group that did this, we try to first, so once you get these materials that MatterGen predicts, for example, or that Miguel's model predicts, you basically train some models to predict whether they have TC. And we can train them, and we can get a good, comparable with the best reports in literature, R squared, etc. By putting some classification heads. It's not important due to the shortness of time. I'm not going to get into what we do. But then what we ask MatterGen is to generate materials and to generate, in particular, superconductors. So then there's two things that it does. So first of all, since it's based on diffusion, it's just going to generate materials based on distribution. Now, most of these materials, if you let it generate enough materials, it's going to generate billions and billions and billions if you have time. The ratio of stable, unique materials will go to 0 in the end. And what you need to do is, and this is very important, is you need to run afterwards a machine learning force field to actually make sure that some of these, 99%, if you let it run infinity, most of these materials are going to be just complete disaster. So you need to run machine learning force field to actually make sure that they're stable. And these machine learning force fields are actually trained on Miguel's data. They're actually trained on DFT data, so they wouldn't exist without Miguel, right? Okay, so we do this, and then we get some materials, or E and Hangshi get some materials that are basically close enough to the convex hull. These are 60 or 80 electron volts above. Diamond is 100 something above the convex hull. So it's okay. Okay. So but look what it does. So you can understand what it does. You can say, oh, this looks a bit different. But what it does here is it knows that zirconium nitrogen, ZRN, is a superconductor because we trained it on it. We found out. Then it quadruples. It's in a different symmetry group, but it's in a symmetry group that's above it. It quadruples the unit cell by going to a lower symmetry group, and it substitutions one element to this. So I would say this is also not incredibly new. We want something completely new. Okay, so with that, I think I'm running out of time. I have some example about understanding AI from Lave phases, but the moral of the story is that generating materials with MatterGen will most of the time give you nonsense. You have to run them on these programs that are actually trained on DFT. But even then, from what we found, there's still the question of whether it gives you something really new or just makes a lattice distortion and then substitutionalizes some elements. So that's an ongoing effort. Thank you.
Thank you.
You know what to do with microphone.
Is now on, I think. Okay, so thanks for the very nice talk. I just have a question about the diffusion model. With images, you put pixels into the diffusion model. What's the format of the materials here? And then you need also features, right? You need the TC, you need the, because like.
So so basically the way it runs is the diffusion model, it has some, you put in some, equivariant representation of the lattice, and you can choose what to put in, and what descriptors to put in does matter, and we're always looking for better ones. We're trying to put a covalent descriptor that we're trying to get from this MGB2 thing. But in the end, it's going to generate a material. This is not yet conditioned to generate high TC materials. You then run it through SodNet to predict whether it generates.
So the model doesn't know anything about the TC of the material, just has the equivariant.
This one, well, there's people that did condition it on TC of the material, so you can skip some steps. But right now, what we're doing is we're doing the most basic thing, just getting our hands dirty, and then we run it through the machine learning force field to get the stable ones, and then we run it, or Ian Hangxia run it through the TC predictor to get some TC.
So if Miguel did the one with the conditioning on TC, does that do better, or that really it's the same issue? It just really does a small substitution and dopant or whatever.
Well, that's a question for Miguel. Okay. but I think there's still issues, in my view.
Thank you.
Okay, Paul. Just one question.
Criticize.
Go ahead. Yeah.
Criticize.
I can talk about AI, but let's start with outliers, okay? Did you look at yttrium, palladium 2, boron 2, carbon, which has a TC of 23, or the related yttrium, nickel 2, boron 2, carbon, which is stable, which has a TC of 17? These are not MGB2, but they rivaled the highest TCs of electron phonon in 97. I'll mention them briefly on Friday, but that would be another one to test on. If you can get it, awesome. If not, it gives you a second one to focus on.
So here's the thing. So Paul. So basically, we tried to look at a couple. I'm not sure if we looked at those, but what we tried to do is look at something that has a very simple band structure. Of course, we can look at something that's more complicated and then run DFT through it and numerics. But we try to do at the this is the 0th order of a hopefully 6-year effort or 7-year effort. But what we try to do at 0th order is to look at something that's simple, like MGB2, which I can get things analytically by pen and paper. So if those are complicated, have complicated band structure, then we didn't.
There's thorium, chromium 2, silicon 2, but that's fine.
We would love to have a list of, that's why it's good that you're here. We'd love to have a list of all these outliers to look at more analytically.
Okay. So I'm going to avoid AI for now, but let me make one other comment. Part of the goals, which you flashed up and assumed everyone saw yesterday, some of us weren't here yesterday.
Oh, sorry.
But if part of the goals is to, try to find useful new superconductors, whatever, the one thing I see missing that you might be able to do is also HC2. Some materials respond very well to doping and increase HC2. MGB2, you can double HC2 by adding a little carbon, okay? Borocarbides, you can dope every which way and you can't change HC2 for love or money.
I see.
And if you're starting to think about this, that's something I would add to your agenda and should be touchable. I'm not asking you about pinning. Pinning is way extrinsic. Give it up. But HC2 is, I think, in your purview.
I think Miguel is working on that, right? On HC. No? Okay.
No.
Okay, then you're not. Well, we should be, maybe, all of us.
Okay.
Going back to the case of the cadmium nitrogen chloride, that we cannot get the TC right.
I think the ones we do know, right? Are they considering spin-orbit coupling? No, right. But you know, so there are papers that claim to get the TC right to some RPA, etc. But you know, I don't know how accepted they are. They have like 10 citations.
I raised that up because looking at the structure, right, this looks like a locally non-central symmetric system, so there will be some spin-orbit coupling that momentum dependence there. And if we are maybe transferring some of the recent knowledge on STO, that for the quantitative aspects, spin-orbit coupling might be actually be very important. Maybe that's the homework that we need to do here to get it quantitatively right.
I see. So okay, so we can talk afterwards. I think that one of the main reasons why electron phonon coupling doesn't give you any large thing here is that this band seems to be zirconium, right? And the largest phonon is nitrogen. So there's a mismatch somehow between these, which suppresses. But we can chat about. I mean, he actually know better the numbers for SOC. I can't quote them now. In this, at least the DFT numbers. Okay.
And you mentioned that there are thin film results on MGB2 that have the right trend in temperature. What's the nature? How's doping done there? You said something about strain.
So it's not doped, but since it's got two Fermi surfaces. It's got the PZ and the sp2 Fermi surface.
Right.
So if you strain, they're going to respond differently, and one of them will go down, the other one goes up. The sp2 one gains electrons, so the Fermi level goes up towards the point in that scenario. So it's not really doping, but it's just the strain, because it's a multi-band, influences the two Fermi surfaces differently, and basically effectively dopes the sp2 level.
Hi. Right, three things. First, on the subject of HC2, the thing which is theoretically accessible is just the superfluid stiffness which you have your hands on. Roughly speaking, big HC2 translates into big superfluid stiffness. So I think Paul's question on an order 0 theoretical level should be answerable.
But we don't have a database with a superfluid
stiffness
of the...
that's the direction to go. That's all I'm trying to say.
Yeah.
As a piece of unsolicited advice, I think you should learn to talk faster and put more interesting results into your talks. And so that's clearly revealed by this. But to that end, I missed, possibly because of a microsecond attack of narcolepsy, what you said about bounds on superfluid stiffness. Can you amplify a little bit?
Yeah, so it's bound. We're trying to bound. So it's the superfluid stiffness. We don't. So yeah, we don't have a bound on TC. We were trying. We're hoping to have one, but right now what we're trying to do is bound lambda. So the bound. So this is assuming. So this is not a bound. This is an approximation, which makes a lot of other approximation. In particular, it's an approximation when the electron-phonon coupling is due to changing of the hopping. So it's a partial T. It's not a Holstein. And then
Look at the whole.
oh, okay. And then what you realize is that if the hopping scales exponentially, which the exponent is this gamma, and the phonon frequency is omega, etc., then you get these are basically like Kohn-Sham type bounds. This gap bound. So you get this dispersion. So this is a Fermi surface, and you get these bounds, which you can think of this as the, obviously it would be the quantum geometry if M would be a flat band, but it's not. So it's an approximation, it's not a bound.
But just intuitively, how much do you have a sense in general for how much more buffer geometry for the lenses that I care about in superconductivity, or is this still too soon?
So we claim that for MGB2 is 92% of the entire lambda, the geometric one, i.e. the one that comes from the derivatives of the wave functions.
But that's for the pocket right here at the beginning.
But that pocket has 90% of the superconductivity. So that's the crucial thing. So that pocket is just dominant, and out of that pocket, 92% is geometric. That's a very good point. Yeah, thanks.
Yeah.
I hope this is a useful comment, but Ziek-Shen has shown that he could measure directly the electron-phonon coupling. He did this in, I think it's iron selenide. They managed to whack it so that some phonon starts oscillating. Then with ARPUS, they watched the energy of some level oscillate. And with X-rays, they watched how big the phonon displacements were. So it's a direct measure of the electron phonon. It turned out to disagree quite a bit with DFT, but it could be fixed with.
For which compound?
I think it was iron selenide, but
I see.
what? Yeah.
Was it still small?
What?
Was it still small? Yes.
I don't know. It was quite a bit bigger than LDA said. Yeah. Okay. Yeah. So okay. My point is that one might imagine if things, if there's a benevolent deity, that you could do the same thing with this. You could maybe do pump and probe with some optic measurement that could see how the wave functions of the states at the Fermi energy oscillate. So there may be direct ways to measure these things.
EPC, the
What?
lambda, or the electron-phonon coupling.
The electron-phonon coupling.
Integrated over the.
Yeah, no, but also to measure the different pieces of it by just doing a different measurement than he said. So he saw how the energy modulates. So that's measuring the first term in the electron-phonon coupling that you were talking about. But I don't think it's out of the question that you could measure the quantum geometry part of the electron-phonon coupling the same way.
Right.
And as I said, for the first part, you had to go well beyond LDA. LDA really didn't work well for this.
Right, but that's so we're not so far. That's why we completely in our TC prediction we completely removed all the things that might have electron-electron interactions. We're just trying to understand the electron phonon in the ones that hopefully don't have any. Right, so just because So that's so.
So this is just a much more direct way of measuring whether you're on track or not.
Does that exist? I guess you need to cleave it, right? Well, it needs to be.
I mean, you need to be lucky. You need to have a phonon that'll ring.
Paul wants to say one phrase. Then, yeah.
Still making single crystals of MGB2. It's available if you guys have a clear prediction, actionable or whatever, of trying to separate these. It does, exfoliate well, not exfoliate, it does cleave well enough.
Does it cleave to how many layers? Well, not
No. Cleave is.
You can't exfoliate it, right? It
No,
doesn't.
you
exfoliate,
cannot
right?
exfoliate,
Yeah.
but you can cleave and get a clean one for ARPES measurements. Kaminsky's been doing it in-house with various doped ones. But this is actionable. If you guys are able to come up with some statement or experiment, that's something the sample can be provided.
I think
Okay?
that can be done for MGB2 because.
What?
I think that can be done.
Well, then.
Because it's not a doping prediction, but we can predict. We can predict other things for the Fermi surface.
Do it, and we can try it.
Yeah.
And it might be ultra fast or otherwise, but that's doable.
Okay, the last question.
But what?
Yeah. Have you, you complained that sort of the materials you're generating are just sort of maybe interpolations of other materials that have been found. Have you tried generating data from sort of tails of the distribution, like 3 sigmas, because your distribution is ultimately noise, right? You go from noise.
That's okay. So first of all, I didn't complain. It's just a remark. I never complain. but so that's what we're doing now. We're not. So you're basically saying to generate. Don't start from a random distribution. Just start from something that's not random, but it's got some noise in it, right?
What I'm saying is, you have this generative model, and you map from noise to superconductors, right? The reverse process, right? And so it's just take data from the tails of this distribution, let's say, and see if that gives you sort of more unusual states. Have you tried that? And does it return garbage?
I think right now it would give you. Garbage. If you So we're doing something similar, but it just involves on just starting with the. Anyways, it involves starting with some intermediate state, not just noise.
Okay.
So that's what. But I think, yeah, we can talk about it.
To end on this point,
do
but
it.
you started with trash cans, so it's
Okay.
okay.